subsidence. I did say the levels were written on the stuff, so the first thing I would do is send somebody to take the levels, check if the same levels exist. And the best part was we knew it hasn't changed a millimeter. The level that they recorded was exactly the level after 80 years. So that means the structure, the piers haven't moved an inch. It's great. And strength, they've recorded the strength at several times during the 80-year span. And we had a collection of that data. Sometime they have actually taken a core and looked at the core and they said river pebble was used in construction. Okay. River pebbles are the round aggregates. They have no particular shape pattern other than being just circular or oval. So, and we know where the river pebbles came from, just from the structure itself. They've dug the foundation, they got the river pebbles from the river, they used that for construction. So we could see the story slowly evolving and unfolding. And this is why I was saying that you need to look at the material properties. And if anybody has taken a picture of it, great. Traffic is critical because I need to know what's the actual traffic on the structure before I put out a massive rehabilitation program. If you do all of that work and there's still 4 cars and 5 lorries and 2 trucks going through it, what's the point? Okay. So thankfully in the UK they've been collecting traffic data now for a couple of years now. They have things on the road, like 2 rubber tubes on the road, so as vehicles go through they can look at the pressure change in those tubes. The time between the pressure changes gives them the span of the diameter of the tire, and the value of the pressure change tells them what vehicle load, and the next hit will tell them how big the vehicle is. And they're using clever systems to figure out, oh, that's a truck of certain load. They're collecting this data on a million data per month basis. So all they're trying to do is to create a histogram of loading. These are the extra heavy vehicles, the number and the weight of them. These are the extreme light vehicles. Okay. It's just the frequency of these things matter. So if the frequency of these heavy vehicles increase, we have a problem. The structures can take, it's designed to take 40 tons. It could be somewhere here, 40 ton. And it's designed to take 40 tons in a certain frequency. But if the 40 ton vehicles increase in frequency, the strain on the structure is quite high. And if more heavier vehicles go more frequently, that's also a problem. Okay. City traffic tend to be on this side, so it's manageable. But these are northern periphery regions, so you have a lot of factory traffics going through. There's a lot of recycling plants up in the north as well. So every now and then we can see in the middle of the night a 60-ton lorry going through. There are no 60-ton lorries, so it's basically overloaded lorries going through. They would only go in certain time, and we know the time that they will go. So all of that. Okay, so this is the minimum things that you gather without having to sweat, really. So let's see. And then you need to figure out the importance of certain region and importance structurally of each member. Even from the beginning, we knew that as long as the edge beam and the transverse beam remain in place, failure will be localized. And that gives us confidence that localized failure means a lorry's tire might actually get trapped. The lorry doesn't go into water, that's okay. It's not going to be damaging. It will be damaging, but it will be just paying the lorry, not paying the whole thing. And that was our attitude to the structure as well. Our priority was to check the edge beams and the safety of it, and also our priority was to rehabilitate, if needed, the transverse beam. Some of the secondary beams, especially around this region and here, were beyond repair. I mean, we were able to remove part of the beam by using a timber. We just hit it with the timber to collect a sample, so it was that bad. Corrosion was prevalent. So about 3 meters from here is the first construction, or the bay joint, construction joint. And alongside that, the rebar has nearly vanished on the edge beam. Okay. So the next thing is close inspection as part of the special inspection. And we had to bring some form of vehicle. This is not the exact vehicle. We had to bring some form of vehicle to do under bridge inspection, because most of the damage in our case is under the bridge. It's a very tricky business for two reasons in the structure. That's between 12 and 18 tons. Bridge can only take 3 mathematically. So we had a problem. So we had to do calculation to figure out one-time loading on a closed road basis, can they be on the structure? We did a quick calculation and figured out that should be okay, as long as there are no more of them. Okay. So we let an under-bridge inspection system to come in. A special investigation report was commissioned. It was awarded for 12,000 sort of pound. It's around 10 lakhs in your money. And about 7 of that was for the vehicle. Because the vehicle we had to bring the vehicle. The vehicle had to be brought from England, and it had to remain nearly 5 days. 3 days on site, 1 day coming from England, 1 day going back. We were paying for all of that. So we knew this is going to be a costly business, but remember the contractor charged only 3 or 4 lakhs, 3 something lakhs, 3 point something lakhs for doing the inspection. So that was extremely low cost. But they had their own ideas, because they know this bridge is now going to repair. So if they have a close inspection, they've carried out close inspection, they know they're going to get the next stage of the work. So anyway. So it's a 2-engineer job. It had to be very, very fast, and we managed to get most of the information. So this is how the bridge looks like when you draw it out. The river, quite deep and fast flowing. This is why I was concerned about the levels and the safety of the levels. Quite often in rivers you get a timber logged into the piers, and that means that pier now is taking the entire horizontal force of the river. So imagine a timber got stuck here. So it's not just water going around it, it's just the full water pressure being taken. So all of these are concerning stuff. It's part of the regular maintenance. These colors that you're seeing, see the line that you're seeing here and the vertical lines? That red line is the crack on the horizontal edge beam, the 2 meter beam. And that's the same level as your deck. So all of these will tell us the story where we're going with it. Okay. And there was a massive crack here originating from this side, going up to the crack on the edge beam that went further. What does that crack indicate? The one here. Does it give you a telltale indication where that crack is going, or why the crack is there? But you normally suspect shear. Okay. But that's what the first inspection, the structure came up for inspection in the first place because they suspected shear failure at that point. We had our reasons not to believe it, but it's been highlighted, so that's an issue. That's a more close-up view. It's an 80-year-old structure, so you're going to see a lot of information. You need to filter it down and get through the information you want. There were 2 line cracks all over. These horizontal cracks were more concerning for us. Okay, I'll come to that. So any other major things I need to note from here? No? Just feel free to ask me the question. This is how the half cell potential mapping looks like, and that's probably what we normally do. So the individual values are recorded here. Different color means different test, but these contour maps indicate the half cell mapping. Okay, sorry, these contour maps indicate delamination, and the individual values with the color indicates half cell. what we were looking at is wherever half cell changes from positive to negative, because that boundary is interesting for us. That means there is an anode and a cathode somewhere there. And that's the two colors. The red means it's negative, and the yellow means it's positive. And these are spalling spots. The blue probably means the new spalling between the last and this inspection. There was another inspection carried out earlier, and that could be an old one. These lines are the cracks. So you can see the bay joint here. There's some form of bay joint here, not evident. There's full cracks here. There's another joint there. Okay. You can see some of the staining. This was an older photograph. By the time we went back to the structure, this you could see the reinforcement. The cover was completely gone. Anyway, I wanted to bring you to here. This is the edge beam, the cross section of the edge beam, okay? And that's your 2.2 meter thing, roughly. Okay. So, can you gauge the size 44 mil bars? How big 44 mil bars would be? That size, okay. We had 4 of them on the top. We had 4 such layers on the top. This is closer to over the pier or close to the abutments. As you come to the middle of it, the top bars reduces anyway. And the bottom also had 4 bars, 44 mil bars. To keep everything in place, they had 6 shear lines. Okay. Do you think that structure will fail in shear in concrete? I don't think so. I personally call it a steel structure coated with concrete. Essentially, that much amount of steel was there. And that's why the history is important, because Hennebeek system, when they converted from the typical Hennebeek system where you have the steel underneath the concrete and concrete above it to steel inside concrete, they were doing that to the teeth of it. They were overdoing things. That's because there was a lot of failures along with it. So this structure was designed almost like a steel structure. And that much amount of steel would, if you look at the I-beam, that's enough to create I-beam and a half at such a great live around. So which means the structure is, edge beam is not going to fall. The only thing is if the deck is going to fall around it. This is the deck. Okay. So the deck had a surface like that, obviously, a road surface. Water was coming here on the south side, and water was clearly going between the two and then going out. And that's why you saw stains. When you look from here, you saw stains in a horizontal line. That was there. What is the concern with that? What does that structurally affect? It's away from the two main reinforcements, so that's okay. But it does affect us some way. How? So, to give you an idea of it, I know these questions are annoying, but it keeps you awake. So this is the structure, and that's the deck, and this is the road surface. Okay. So what we were expecting was water was coming in. Because the drainage was tilted towards the south. All of these were coming towards the south and going in between it and then getting out. Okay. It wasn't jumping out because it's a big structure, but it was causing enough damage here that we could see a big rust stain here and a lot of leaching alongside. That affects my steel, but not the tension or compression steel. In this case, that's the tension steel. It affects my shear lines. For such a large structure, if the shear reinforcement is affected, I should be concerned. Okay. So these were the concerning aspects when we went into the structure. But we were able to draw this out from the actual as-built drawing. or near enough as-built drawing. So that was a good starting point. That means I can do assessment quite easily. And the edge beam, the tiny secondary beams looked like that. It had a 22 mil rebar on either side, a 9.5 mil circular perfect ground bars. And there were also 2 bars on the top. Didn't needed it, but they actually had it at the top. Probably they needed it for the shear links. We checked a lot of these. Some of these were quite easy to check because they had no cover, so you could just look at it and get a vernier calipers to get the gauge. This we also checked by drilling into it. We removed the top surface to figure out if there's top bars because we needed the compression steel later on. And the cover was set to be 25, but we hardly had 10, 15 mil in times. Okay. So as anybody else would do, we just put the structure into a finite element sort of model. Run the finite element model, so you'll have closer meshes to the edge to capture the inclined beams. And then we analyze it and we get the load. See, the reason for using that kind of structural analysis package is that it can do different scenarios of loading. So it can do a 40-ton loading, it can do 28 or 12 or even special vehicles. All it provides is for each node in the structure, it provides a high bending moment and a high shear force. And from that we check the capacity using hand calculation. So the calculation works this way. Stress index or safety index, whichever you want to call it, is a ratio. Okay. Ideally it should be 1 or below. Okay. So that means your capacity needs to be on the bottom and your actual loading or actual bending moment or actual shear force should be on the top. Okay. In most cases we prefer that to be 0.8, less than or equal to 0.8. That means we have 20% redundancy. Remember, this is the perfect structure. It has no durability concern taken into account. So if it is greater than 0.8, we're assuming that there's a bit of redundancy with the structure. So we do that for every single node, every single concerning node, to be honest. So node or element refers to these tiny things. So it takes weeks and weeks and weeks and weeks of calculations. Or you can just rely entirely on a structural engineering, structural analysis package. It's up to you. Gain its own confidence. I decided to go the hard way because ultimately I had to sign saying this is okay. And also I wasn't familiar with structural analysis at that stage other than my undergraduate knowledge. So we did all of that. There were a few people who checked this stuff later on. And at the end of it, we came to this. And this is what the client wanted. 40 tons HA loading, 2 lanes. They wanted to know what repair do you need to do to make that happen. So I had to project the stress index onto the structure to convey that message to the client and say these are the areas that will be stressed, this is the kind of repair I probably will need to do. So 40-ton HA refers to 2 lanes being open. 40-ton vehicles can go on that. It does not mean it only has a 40-ton. If you look at the loading pattern, it will show there could be different 40-ton lorries there. Okay. So it's a reference to a loading arrangement rather than one load. Just bear that in mind. So HA refers to a normal loading pattern. HB refers to special vehicles like big cranes or something that you're moving around. Okay, so 40-ton HA loading means these are my stress points. So the red indicates stress index is more than 1 for shear failure. Okay, and this is the bright spots indicates stress index is more than 1. A bit of hollow spots indicate stress index is It's in a safety margin between 0.8 and 1. And that's for shear, this is for sagging, this is for hogging. Okay? It's all because we can convey the message quite easily to the client who's a civil engineer, structural engineer, but they're not into the business of all those calculations. Okay? So you can see that shear failure can be dominant and are very critical members. So that's not a direction I'm going to take. Okay. When we presented that work, and then I had to present other things as well, so 18 tons, 2 lanes was the next option. And we did try 28 as well. You do still have shear failure possibilities, but that's now concentrated in a very small region. Only this region had the issue. Everywhere else you had a small redundancy built in. Okay. Except this region here where we needed a bit more hands-on action. So this is where the structural analysis will need to go hand in hand with the durability work. Okay, so durability hasn't arrived yet. Okay. So at the end, what the client wanted was ultimately 2 lanes to be open. They were happy if the 2 lanes were 7.5 ton restriction, which is 7.5 tons normal for a lot of those bridges around it. So they were happy if we say 7.5 tons, 2 lanes open, and that repair they were happy enough to pay for it. So that's how we went into tender. We said 7.5 tons, 2 lanes has to be open. Whatever repair schedules they believe they can do that'll achieve them 7.5 tons, 2 lanes will be accepted. Does that make sense? That's what we said. Okay, so along with that, it's tender's responsibility to say what is a good repair. We have to draw it out and say this is what a good repair is. So I take it that's what your guys are really interested. So, and tender documents are massive, like lines and lines and lines of tender documents. So for the edge beam, which was in that shape, we suggested these edge beams to have to expose the shear connections without damaging them, and to find out what they need to do to make good. Okay. In concrete, most of the shear is carried by the shear reinforcement, and in large cases we know while concrete can take the shear, they really don't. We don't assume that they take the shear. We just ignore that and go into the